A cubic spline is defined by a standard polynomial equation, mapping a curve in space based on a parameter, t. By convention, t ranges strictly from 0 at the start of the curve to 1 at the very end. Navigating complex geometries rapidly and safely requires precise physical control over the object's position at any given moment. But the parameter t creates a mathematical illusion. Advancing t in constant uniform increments does not produce uniform physical motion along the curve. Moving at a constant rate of t, a point's velocity vector dynamically scales, accelerating through straights and decelerating sharply in curves. T is a mathematical weight, not physical distance. Consequently, taking equal steps in t yields highly unevenly spaced physical positions. Relying on t to dictate movement breaks physical predictability. A virtual camera tracking a target will unpredictably hitch, and an industrial robot told to move at a constant t rate will over-torque its motors when attempting to navigate a corner. The engineering objective is to solve the inverse problem, establishing a pipeline that accepts a specific target distance, s, and outputs the exact corresponding parameter, t. Finding that physical distance requires continuous calculus. Specifically, we must integrate the magnitude of the velocity vector with respect to time. The formal integral required to calculate arc length expands to reveal the underlying geometry, the square root of a cubic polynomial's derivative. Integrating this has no closed-form mathematical solution. Because it cannot be simplified, it is impossible to rearrange variables to isolate t. Continuous calculus natively prohibits a clean solution. To control physical speed, we abandon pure continuous algebra and construct a discrete two-step numerical workaround. The first step is to approximate the area under the velocity curve to find the distance. This line graph maps the continuous velocity magnitude on the y-axis against the parameter t on the x-axis. Basic trapezoidal integration slices this area uniformly. This is computationally inefficient, creating jagged error gaps and severe overestimations at the steepest peaks. A mathematically optimized alternative is Gauss-Legendre Quadrature. Instead of uniform slices, Gauss-Legendre dynamically spaces its evaluation nodes, clustering them intelligently where the curve's rate of change is highest. Specific mathematical weights apply at these exact nodes, capturing the exact volume with a fraction of the calculation steps. The output of this approximation is a definitive list, specific physical distances directly mapped to specific t-values. This data table displays a lookup table, or LUT. It acts as the storage architecture, holding these pre-calculated pairs of distances and parameters in memory. Running the heavy Gauss-Legendre approximation offline and caching the results into a LUT ensures that live frame rates remain completely unaffected during rendering. In real-time operation, the engine requests an arbitrary physical distance s, and the system must retrieve the unknown t. The algorithm scans the LUT to find the two pre-calculated distance values that bracket the requested target. This scatterplot visualizes the LUT points in mathematical space. Drawing a straight line between the two closest points generates a fast initial guess, t sub 0. Because the true relationship is curved, this straight line inherently produces a small error margin. Linear interpolation alone is too inaccurate for flawless simulation. However, for a microscopic computational cost, it successfully narrows the search radius. To eliminate that remaining error gap, the system passes the linear guess into Newton's method, an iterative route-finding algorithm. This graph displays the true nonlinear curve for s of t, with our initial guess t sub 0 sitting slightly off the target line. Newton's method evaluates the slope of the curve at that specific guessed point to project a new, highly accurate coordinate. The formula refines the guess using the difference in distance divided by the derivative. The tangent line at t sub 0 projects downward, intersecting the target line to define a closer point, t sub 1. Rapid iterations drive the error gap down to absolute 0. The mechanical efficiency of this process relies on one specific fact. The derivative denominator in the formula is literally just the velocity magnitude. The engine already calculated the velocity equation when generating the spline initially. Executing Newton's method here requires almost zero additional processing power. By pairing a cheap LUT search with Newton's surgical precision, developers solve the inverse problem within tight real-time constraints. Returning to the initial failure state, motion governed strictly by constant increments of t is erratic. This split screen compares both methodologies. Left, naive motion using t. Right, engineered motion using uniform distance, s. The pipeline fires every frame, transforming distance requests into verified parameters. Entering a hairpin, the left object violently accelerates, while the right maintains flawless, constant physical speed. In hardware robotics, this architecture prevents erratic motor torquing, ensuring heavy machinery follows three-dimensional toolpaths with exact timing. In digital cinematography, it empowers virtual camera rigs to execute sweeping, unbroken tracking shots without a single microstutter. When continuous calculus presented a dead end, engineers knocked the geometry discretely and executed a rapid, localized search to find the correct coordinates. True control in physical simulation demands that the continuous illusion of mathematical time is deliberately decoupled and re-engineered into measurable physical distance.